Hello, everyone. Today, we're talking about adversarial robustness of large-scale audiovisual learning. This is a joint work between my collaborator, Shuhui Chu, Xinjian Li, Poya Huang, and my advisor, Florian Mehta. As we all know, these days, there are more and more safety-critical tasks that requires audiovisual event recognition, such as surveillance cameras, self-driving cars, and also online filter for a lot of large-scale companies, right? But such models, their robustness are not clearly understood yet. So in this work, we're taking a step at this problem. Let's first look at dataset that we're looking at. And a lot of audiovisual data are coming from YouTube. Namely, the most famous one is AudioSet in this area. So it involves 2 million to 10 seconds long audiovisual samples from YouTube that contains 527 different classes. And we also work on kinetic sounds in this paper, but the results are very similar to AudioSet, so we don't separately report it in the slides. You can check them out in our paper. The task here is to predict the semantic label of an audiovisual event, such as applauding or clapping sound, right? So as you can see, intuitively from the log-mail spectrum, they look very different. Each class looks so different from each other, and they span a wild range of frequency all the way from 0 hertz to 20,000 hertz. And they're very different from human speech is only one subset of such cases. So also a little bit of background on adversarial example. You must have seen this picture where adding a bunch of noise to a pig that is almost invisible will change the machine learning classifier predicting from a pig to an airliner. And we also showed in 2019 that by playing a piece of music, specifically crafted music alongside Amazon Alexa, will trick the wake word not into waking up the model. How do we do that? The fundamental idea is actually pretty simple. Instead of minimizing the loss, which we were used to do when perfecting the model to have better accuracy, we leverage the adversarial perturbation to maximize the original loss so that the network is not able to do well under the influence of this adversarial perturbation. How do we fend off adversarial perturbation? That's the holy grail of studying basically adversarial robustness. And the community has been looking at point-wise robustness extensively since 2018 till now. It's been multiple years. So the effort was really about provable defenses that characterize convexity by relaxing the non-convex network into convex network, so you can derive a safety boundary alongside the original sample. Taking it to extreme, 2019, Matt Jordan developed the framework of a centered Chebyshev ball, so that the essential idea is to formulate as a convex program to find out the maximum allowable radius of that ball that allows the decision boundary to stay wrapping around the maximum allowable radius of such sample. But such point-wise robustness work is found to be non-scalable because they involve very expensive computation time, and also it is hard to realize on non-convex networks. Most of them only work with convex or linear networks, which is not very practical. The actual practical way of doing protection is adversarial training, which the Marjorie lab has done extensively. But the problem with adversarial training is also it's very expensive first, and also you have to take a very heavy penalty when adversarially train on certain data set, which means the adversarially trained network will be naturally with a lot less performance than the cleanly trained model. In such, for example, here, you can see the adversarially trained ImageNet model is almost 20 points lower than the original ImageNet model. That's a heavy penalty to take. So we're trying to address 3 questions. First is, are multimodal models necessarily more robust than unimodal models? Our answer is not necessarily. So let's revisit what is a multimodal adversarial perturbation first. We just talked about how to maximize a loss. And the only difference here in a multimodal setting is we have audio and video input in our case. So you have multiple cases in multimodal models. And here is the formulation of audio perturbation, video perturbation, and a multimodal perturbation, where we jointly optimize for audio perturbation and video perturbation. So the things gets more complicated when we have a non-convex decision boundary fused with non-convex decision boundary. It's still going to be non-convex, unfortunately. So in our paper, we proved that there exists a sample that is unimodal that can break a multimodal fusion network by changing its prediction label from the true label Y to something that is not. We offered this proof in our appendix. You can check it out in our reference section. So a little bit more information about the network at test in our paper. Essentially, those are 2 branches of a convolutional self-attention network, which means they have a convolutional bottleneck tagged along with a few layers of transformer blocks to do the temporal, to remember the temporal information, and eventually their bottleneck embeddings get fused together. So the second question here is, can we effectively or efficiently measure the robustness of multimodal learning by some other metrics than what Marjorie have done on reporting just a score on the downstream performance? So previous work only focused on pointwise robustness, as we just talked about. Our suggestion is, I think we should look into the classwise robustness, which is actually the classwise distribution of a model prediction on a certain data set. That might be a cheaper way or a better angle to look at the problem. So first metric we came up with is called centroid-based density metric. That shares the same intuition with k-means, but in a high-dimensional setting. So in a high-dimensional ball, so we assume everything or the data set are basically a bunch of clusters in a high dimension that also conforms to a high-dimensional ball. Each class is one of the high-dimensional ball. So the intuition is that the denser the ball, the more robust it should get. So following such intuition, we develop a metric that is acting accordingly. So penalize on the samples that fall outside of this ball, and then encourage the basically rewards, this metric rewards the whatever classes that are densely concentrated around the centroid of those classes. So the second metric here is called the convexity-based metric. Convexity here in the neural network case carries a little bit of different connotation than the classical convex optimization. For example, here, specifically, we look at the example on the right-hand side, where you connect 2 dots randomly together in a joint embedding space, basically the bottleneck feature layer of a classifier, for example. So if any of the points that are on those connected dots are falling outside of the decision boundary, then we call them non-convex samples. Whereas if it's still within the decision boundary predicting the same label YC, then we define them as convex samples. And we model it by aggregating the indicator function's output so that we can get a KC. The higher KC is, the more convex the decision boundary of class C is. And we should expect more robustness from this. So naturally, how do we leverage these different metrics to serve our purpose to develop a better strategy for achieve more robust models? Our answer is pretty simple. We leverage mix-up, and we leverage in a way that is empirical. Basically, we have a threshold for convexity and a threshold for density, so that less convex classes get mixed up with denser samples. So we balanced the entire training set out by doing such a mix-up. And we expect the model will learn better, more robust models from this kind of training procedure. So we did a lot of experiment to sort of verify our findings. This is the picture of the table, the correlation between performance drop after adversarial perturbation versus convexity. As you can see, the performance drop rate is calculated by clean performance minus the performance under adversarial perturbation over clean performance, which means the less performance drop we get, the more robust the class is. As you can see, so the right-hand side, the lower corner are the most, basically the lower the vertical axis, the better robustness the class will have. And interestingly, we see music and speech, which accounts for nearly half of the training samples in the audio set, are very robust classes. All the siren classes such as siren, civil siren, fire truck, police, emergency vehicle, they're all very robust classes. And on another note, the red number in the tuple that are indicating density scores of classes. We don't list everything out because of the space limit, but you can see the density, the higher the density metric, despite some of being very non-convex class in this case, they're still very robust, such as whistling, telephone bell ringing and stuff. So both metrics are working as what we designed it to be. And this is the final result. So we start with two clean model, unimodal clean model, and then multimodal clean model. The clean model unimodal audio achieves 38.3 MAP versus audio visual model achieve 42.7. So first thing we see is by attacking each model with a single modality attack, what will happen? So unimodal audio model drops to about 18%, whereas the mid-fusion model will only drop to 33.9. It means the multimodal models are slightly better in general than unimodal counterparts, but they still can be affected by the unimodal attacks, which kind of prove our points in theorem 1. To note here, all the attacks are calculated with the same amount of attack budget, which means they all share the same parameter for a number of iterations, step size, and the same epsilon. You can see with the same attack budget, audiovisual attacks are more potent than unimodal counterparts. So we don't need as much attack budget to leverage attack from the two modalities compared with leveraging from one source. And you can see our mix-up actually offers just as much protect to the original model compared to adversarial training. We're on par with the adversarial training, and we're a lot cheaper than adversarial training. So this is really a brief overview of our paper. Please read our paper if you're interested. Again, to recap our findings, first is that we claim that multimodal networks are not always more robust than their unimodal counterparts. And we showed that our density and convexity metric could effectively measure robustness of models in a large scale, not just in a small toy example. And our proposed mix-up could be in a potential avenue to serve as an alternative to adversarial training. Thank you for your attention.